Okay, we want to turn our attention now to momentum, and we're going to start off actually by looking at Newton's second law and this whole idea of center of mass. What we have here is a dancer, and she's making a specific maneuver. I don't remember what it's called, but her center of gravity is going to follow a parabolic path, and that's what you're seeing here. Center of gravity and the center of mass are generally the same thing. But notice it's in a different location. It's lower on her body here and higher up on her body here. Also, because of that maneuver, the position of her head seems to remain in place as she makes this jump. You'll see basketball players do the same thing. And the way they do that is they raise up their feet so that the center of gravity is still going up during their jump, but it looks like their upper body isn't moving at all. Dolphins actually do the same thing when they jump for food. If you have a man standing on a tower holding out some fish, then the dolphin will jump up, and in order to grab the fish out of the man's hand, they'll bring their tail up so their head does not continue rising. The head will stay in position and they can get a better chance of grabbing the fish. So here's the position of the center of mass times the mass. Right? So this is the numerator of the center of mass, and that's all going to be that same summation that we've looked at before. But if I take the derivative of this and the masses aren't changing, then this becomes mass times velocity. So when I take the derivative of position, I get velocity. And I'm keeping the mass in here. When I take the derivative of velocity with respect to time, I get acceleration. And so here's my acceleration equation. But what we're seeing here is the individual forces. So what Newton's law is saying is that the net force on a system of particles, and that actually might be a continuous system, although I've written it out here as discrete systems, the force on each particle is the sum of the forces acting on the combination of particles, or what we call the system. Now the important thing here is that all of these forces end up being the net external force. Now there can be, even though I say the sum of the external forces, there can be forces in between the particles. So imagine, if you will, that we're on an ice arena. Maybe there's 3 of us on the ice arena, and in between each of us is a rubber band. We'll label this part person 1, person 2, and person 3. So if person 1 pulls on person 2, so there's a pull in this direction from 1 to 2. Person 1 pulls on the rubber band connecting person 2. Person 2 is going to move towards person 1. But remember, Newton's third law says for every force there's an equal and opposite force. If there's a force on person 2 due to person 1, if that's the action, the reaction is there must be a force on person 1 due to person 2. And when I sum these two forces, they're vector quantities, equal in magnitude, opposite in direction, that sum must be 0. If person 1 pulls on person 3, there's a force on person 3 due to person 1. But Newton's law says, even though person 1's the one doing the tugging, person 1 grabs the rubber band with their hands and pulls, there's still going to be a force on person 1 due to person 3, even if person 3 doesn't grab the rubber band. Newton's third law says that's got to happen. Same thing between 2 and 3. So always the internal forces will cancel out when I sum them up. And so the only forces that count as I look at the entire system are the external forces. There are internal forces, make no mistake, but they don't do anything when it comes to this momentum or net force, either of them. They don't do anything because they cancel out. Now, if I look just at person 1, then person 2 and 3 are exerting external forces. But if I look at person 1, 2, and 3 as a system, then the interaction between those people are internal forces, not external. So we define then momentum as the mass of an object times its velocity. So notice momentum is a vector quantity. Very important. Now mass is not a vector quantity, but velocity is. So momentum is a vector quantity. And another way to express Newton's second law, the force equals the derivative of momentum with respect to time. If you think about that, the derivative of mass times velocity with respect to time equals, use the product rule, the derivative of mass with respect to time times velocity plus mass times the derivative of velocity with respect to time. So I get dm dt times velocity plus mass times acceleration, which I might write as m dot. Remember, dot means derivative with respect to time times velocity plus mass times acceleration. Generally, mass is constant. If you work with rockets, that's not the case, but we're not going to worry about that for now. So usually this term is not something we worry about, but there's F equals ma. So this expression, F equals the derivative of momentum with respect to time, truly is a more accurate expression. But for all intents and purposes, with very few exceptions, we will come across exceptions, but with very few, it will in fact be mass times acceleration. If I have a system of particles, then the net momentum of the system, so this is the system momentum, is the sum of the momentum of each of the individual particles. And we'll see this take place when we look at collisions. And the neat thing is, if we go back to the whole concept of center of mass, remember, center of mass is the sum, I equals 1 to n of m sub I, r sub I. If I look at the derivative of this, and we'll assume the masses are remaining constant, then the derivative of this with respect to time equals the sum, I equals 1 to n, m sub I, v sub I. And this is the sum of the momentums. Center of mass with respect to time, so the derivative of the position with respect to time times the mass is the momentum. And then if I take the derivative of the momentum with respect to time, so the derivative with respect to time, the sum I equals 1 to n, m sub I, v sub I, and we'll assume constant masses. This is the sum I equals 1 to n, m sub I, acceleration sub I. And that's just the net force, the net external force. Very important, the net external force. So if the external force is equal to 0, big if the external force is equal to 0, then the derivative with respect to time of the sum I equals 1 to n, m sub I, v sub I, that must be equal to 0. But if that's equal to 0, then the sum I equals 1 to n, m sub I, v sub I, is equal to a constant, meaning the net momentum remains constant. Even if there's interaction between the system particles, if there's no external force, the net momentum of that system of particles will remain the same. Individual particles might change momentum, but the total momentum of the system will remain constant. Super, super important. But super important depends on this statement. This is only true if the net external force is equal to 0. Okay, so there is a term referred to as impulse, and impulse really is the change in momentum. Notice this equation right here. It looks fairly familiar. It's of a similar nature to work and energy. Instead of kinetic energy, I have momentum. So if a particle has an initial momentum, and there is an external force acting on that particle over some time period, then that particle will change its momentum to some value mv2. So the impulse, which is a vector quantity, and we often use the letter j for it, is equal to mass times velocity 2 minus mass times velocity 1. That's the impulse. Or the impulse is the integral of force with respect to time, integrating from time 1 to time 2. So an individual particle can have its momentum change. An external force is required for an object to have a change in momentum. Now this time factor is kind of important. This goes into the idea behind, say, airbags. Before airbags existed, if you were to come to a sudden stop in your car, you would hit the steering wheel or the windshield. Let's just say the steering wheel. The steering wheel is going to hurt. And that's because when you hit the steering wheel, there's a force exerted on you over a very short time period. Your change in momentum is the same. Your initial momentum is your mass times the speed of the car. Your final momentum is 0. So here's this integral of f dt. If dt is tiny, f has to be huge. But if dt can be elongated, and that's what an airbag does, it makes the time of impact longer. When I do that, I decrease the force of impact. Very important. Same idea when you jump off a table. When you jump off a table, you're going to bend your knees. Why? Because by bending your knees, you increase the time of impact with the floor, and by doing so, you decrease this force. Your velocity just before you hit the floor is the same, whether you bend your knees or not. Your velocity after you hit the floor is zero, whether you bend your knees or not. By changing the time of impact, you change the force. So your body knows what impulse and momentum are all about. Okay, when I have collisions between particles, if there are no net external forces, again, no net external forces, then I conserve momentum. Conservation of momentum. The net momentum of the system is whatever particles are part of the system, will be the same before and after the collision. Keep in mind, that's a vector quantity. If the collision is elastic, then I have conservation of kinetic energy. Okay, that's only in an elastic collision. Conservation of kinetic energy. Okay, a good example of a fairly elastic collision, not perfectly, but pretty close, is a billiard game. When you take two balls and they strike each other, or even three balls, then the total momentum before the collision and after the collision will be the same. A collision that's referred to as plastic means the objects stick together. So after the collision, all of the objects are moving off with the exact same velocity because they're stuck together. So the objects stick together. I refer to that as a plastic collision or a perfectly inelastic collision. Just a little point of interest, if I have two balls of the exact same mass, so billiard balls is a good example. So here's the cue ball coming in, strikes the 8 ball, and the 8 ball is at rest. Two possibilities occur. If the collision is exactly head-on, then the 8 ball will move off with the velocity that the cue ball had. But if the collision is not head-on, the two balls, the cue ball and the 8 ball, will move apart, and the angle of their velocities will always be 90 degrees, something we might prove later on. Again, in the case of rockets, we do have a changing mass, and the whole concept of relative velocity becomes super important. All right, so if you look at the example, you have two sleds. Here's sled number 1, there's sled number 2. So there's number 1, there's number 2. And I've got two cats. You only see one cat, but assume that there are two. And they're on sled number 1. Both cats are on sled number 1, and they're going to jump over to sled number 2. Now, what I'm interested in is the velocity of sled number 1 and the velocity of sled number 2 after the two cats have jumped. Now notice right here, both cats can jump at a speed of 3 meters per second relative to the sled. So this is the velocity of the cat with respect to the sled, not with respect to the ice. That's very important. And if you think about it, when the cat jumps off the sled's going to move to the left. That's going to happen. So the speed of the cat with respect to the sled is equal to 3 meters per second. And it will become a velocity here very shortly. So what is the final speed of the left and the right sled after this takes place? So let's do part A first. Both cats jump at the same time. So if both cats jump at the same time, the cats are at rest in the beginning. So the momentum of the system in the beginning is equal to 0. So the momentum of the system is equal to 0. Now the two cats have a combined mass, so the mass of the cats is equal to 2 times 3.75 kilograms. Put 2 times the mass of each cat. So that's 7.5 kilograms. And then the mass of the sled was 22 kilograms. And so the initial momentum of the system is 0. Well, I have 7.5 kilograms times 0, because the cats are not moving, plus 22 kilograms times 0, because the sled's not moving. So that's the initial momentum of the system. Now the cats jump off. Now they're going to jump, and they're going to have a velocity of the cats with respect to the sled equal to 3 meters per second. But that's not the velocity of the cats with respect to the ice. The velocity of the cats with respect to the ice equals the velocity of the cats with respect to the sled plus the velocity of the sled with respect to the ice. So after the collision, I have 0 here. And in this case, the jump is what I'm referring to as the collision. That's equal to, so I'm going to have 22 kilograms times minus the velocity of the sled with respect to the ice, because keep in mind the sled's going to move left, plus 7.5 kilograms times the velocity of the cat with respect to the sled, which is 3 meters per second to the right, plus the velocity of the sled with respect to the ice, but that's minus Vs of the ice. And all of that's equal to 0. And so I can solve this. I'm going to bring this term to the left. So I get 22 kilograms times the velocity of the sled with respect to the ice. And then I'm going to have 7.5 kilograms, and I bring that to the left again, plus 7.5 kilograms, velocity of the sled with respect to the ice, equals 7.5 kilograms times 3 meters per second. That's this term right here. And if I solve that for the velocity of the sled with respect to the ice, I get 0.7627 meters per second, which means the velocity of the cats with respect to the ice equals 2.2373 meters per second. Keep in mind the sled is moving that way, the cats are moving that way. And then when the two cats land on the right-hand sled, then you're going to have the momentum of the cats, which is 7.5 kilograms times 2.2373 meters per second, plus the sled, which is 22 kilograms, but it's not moving, so they land on it, so that's going to be 29.5 kilograms times the speed of the cats and that right-hand sled. And so the velocity of that right-hand sled will be 0.5688 meters per second. So if I go with significant digits and I have 3, 0.569 meters per second,